Good afternoon, everyone. Thank you for joining for today's webinar. The talk is delivered to you by the International Society for Computational Fluid Dynamics, ISCFD for short. The ISCFD is run by a dedicated team of volunteers, including myself, who aim to increase the visibility of CFD research. Our purpose is to bring people and ideas together by creating opportunities for knowledge exchange, such as this webinar. We regularly host CFD professionals from varying backgrounds to share their work and perspectives. If you like this idea and format, we invite you to follow us on LinkedIn or Twitter for updates. You can also check out our website. And there's some past events on our YouTube channel as well. So please feel free to check them out. I will post all the relevant links for you in the chat. Today's event is expected to last about an hour with 45 minutes of the talk itself and 50 minutes of Q&A. If you have a question, please post it in the chat. That's the standard procedure. I will collect and read them out loud at the end of the talk. So today we have the chance to meet and listen to Dr. Artur Szymański, who is a special guest to me. Artur has joined the Propulsion Engineering Centre at Cranfield University in 2017 as a research fellow in turbomachinery aerodynamics. At that time, I was working on my doctoral project there on water injection. Artur became so interested in the topic that later on he joined the project as my co-supervisor. But back to Artur. Artur has obtained his PhD in turbomachinery design and exploitation from Silesian University of Technology, SUT. Which is located in Gliwice in Poland. Shortly before joining the research fellow position at Cranfield, his research experience combines a wide range of industrial applications, including experimental and CFD projects, broadly in the domain of turbomachinery, fluid dynamics, methods, multi-phase flows, and turbomachinery optimization for the energy transition. Currently, he started a new endeavor and works on supersonic intakes aerodynamics, also within the Engineering Centre for Propulsion at Cranfield University. Artur, it's an immense pleasure to interact again in slightly different circumstances than usual. Without further ado, the floor is yours.
Okay. Hello, everyone. Thanks, Nathan, for your kind introduction. Yes, it's a pleasure. And one more thing that, as I recollect, I was the first speaker for the CFD forum. I think you forgot to mention that as well. So now I'm the speaker for the another one. I'll share my screen now.
Yes, that's right. Before we became an international society, we were locally at Cranfield, and Artur was one of the first speakers. That's actually, thanks for saying that, Artur. It's an important point.
Okay, thank you. Today's talk is going to be about CFD-based compressor modification, supporting energy transition using gas turbines. This topic is not like strictly CFD fundamental kind of research, but it shows you how the CFD can be used in turbomachinery research to support some of the optimization decisions for a very, very important topic that is going on now in European Union and the UK as well as the energy transition. The outcomes that I'm going to present today were carried out with our industrial partner, which is Mitsubishi Hitachi Power Systems, and they were undertaken within the Turbo Reflex project, which is in fact one of the last turbines-oriented EU-funded project, and it combines the experience of 26 institutions, including Cranfield, the companies as Siemens, GE, or Mitsubishi Hitachi that we cooperated. First of all, I'd like to highlight some of the rationales why this project took place and why was it important, what still is. So as you are all aware, the renewable electricity generation is growing at very high pace all across Europe and in the UK as well. But that poses some challenge to the grid that at some point we may have no renewable generation, but few hours later we can get to several gigawatts. On the right-hand side, you can see an example of German grid, where in March, at one point on the time, we can see there's like simply no renewable generation, especially in the night. And then during the day, when the wind blows and the sun shines, there is some renewable generation of approximately 60 gigawatts. That poses a big challenge for fossil fuel technology operators, how to plug this gap between 0 to 60 within very short period of time. And the other question is, what can we do when we have such a high renewables generation? What do we do with those existing rotating machines, turbines, which are typically very high power? A key question that we wanted to answer in this project: how can we enable more renewables on the grid to keep the backup power flexible and ready on the site when it's needed? Here is the contents of my presentation. I'll tell you a little bit on the motivation, then what's important from this point of view of this forum, the methods that were adopted. Then I'll discuss through 3 scenarios that were studied with the CFD. Then I'll draw some conclusions as well. The idea how to plug the gap between demand and renewables generation was relatively simple. First of all, we wanted to know if we can increase the low load capacity of gas turbine engines. So to say, how low can we go with the power of a gas turbine using the technology of air extraction from the compressor. Then we wanted to know how quickly can we restore the maximum overpower settings with the compressed air injection back to the compressor. As you can imagine, this kind of operation poses substantial challenge from the design perspective. Therefore, there were in our university in Cranfield 3 separate work packages that looked at this particular problem. Work package 5 that looked into the engine performance, and there was no CFD used for that work package, only high-level indicators. Work package 1 that I led on, which focused on the compressor aerodynamics, and work package 2, which on the other hand focused on the combustor aerodynamics. And each of those work packages brought some conclusions that were to revise our technology and decide whether it is possible to operate at such conditions or not. So to explain you in a little bit more details, what was the concept? There were in particular 2 scenarios that were investigated within this project. So the first one, as you can see on the gas turbine cross section that we adopted for the study, we wanted to do some research and see what will happen if we design an additional bleed port downstream of the compressor and basically extract some of the air after it. So less air goes into the combustion chamber and then to the turbine, and how it affects, first of all, the compressor aerodynamics, but also what's the local effect, especially near the extraction port of such an operation, and also how does it affect the overall engine performance. Also, the second piece of research that we did was what's the effect of the air injection when we want to restore the power quickly. To do so, we adopted two sets of tools that helped us to research on that technology. The first one was the 0D analytical model, and the second was 3D CFD simulations of the back of the compressor as presented in those two videos. To start with the methods, there were two models, as I indicated. The first one was the 0D model. It was developed in Turbomach, Cranfield University in-house code for gas turbine performance. The right-hand picture, you can see the engine model layout with the compressed air energy storage as a black box system. Really, we didn't really look into the details of the energy storage, injection, and extraction kind of configuration. It wasn't the subject of the project. We focused only on the aerodynamics and the gas turbine operation. The model was inspired with existing Mitsubishi engine, and some of the informations were provided, some of them were assumed, so that gives us a little bit flexibility for the model definition. The model uses the control method of constant combustor outlet temperature, which is here. So basically, the control mode was to dictate what are the parameters in point 14. Also, to regulate the power output, we varied the VIGV, so variable inlet guide weight angle, injection extraction, mass flow rate, and the compressor temperature. Okay, let's move on. As for the 3D CFD model, the idea of the 3D CFD model was to rather inform and supplement the initial 0D calculations. The 3D CFD model replaced the last three stages and the outlet guide way, also with the injection and extraction port if necessary. And the boundary conditions for the 3D CFD model were provided from the 0D model, and the 0D model as such was the source for boundary conditions. The reason why we took such an approach is simply because it's not that easy to have an existing engine that provides some electricity to, I don't know, to a city or steel mill, and then do some experiments. So we need to think first what might happen if we do so, and then try to prove it experimentally. Hence the approach. If we have a look at the 3D CFD model, the geometry of the back of the compressor was provided by our industrial partner. And it consisted of single passage of 7 blade elements that were connected with interstage interfaces. The mesh resolution was such that it allowed for mesh insensitive kind of results with the runs computational scheme with SSD turbulence model with retouchment modification. The set of boundary conditions that was adopted from the zero-D models consisted of total and static parameters at the inlet, upstream of the stage 14, and the mass flow rates in the bleed or injection port and the diffuser. The balance between those two mass flows imposed as a boundary conditions determined the injection or extraction rate from the compressor. There were the blade, the tip gap between blade and shroud was set on of value 1% in each rotor, and we didn't model any hub gaps in the starter nor secondary flows. We focused solely on the effect on the extraction or injection operation. So if you were placed which segment of the engine was simulated with the 3D CFD scenario, it was this cross section here from the stage 14 down to the back of the diffuser. The air extraction that was examined in the study, it varied from 3 to 19% of local flow rate. So it was determined relative to the local flow rate. We also imposed uncertainty on the boundary conditions to account the impact of like performance distortion in the compressor. And we researched for the mechanisms that limit the maximum extraction rate in this kind of compressors. So what we learned first from the performance perspective. The first thing is that CFD model predicted less optimistic results than the zero-D analytical model. On the x-axis, we can see the extraction rate, local extraction rate, and on the y-axis, we see the pressure ratio of the whole segment of stage 14 to the OGV. Depending on the boundary conditions adopted, the maximum extraction rate varied from 12% here to approximately 20% here for elevated conditions. But please bear in mind that the red lines that indicate the positive uncertainty, where the parameters are increased in front of the stage 14, are relatively rare and don't happen that often. We are more likely to experience reduction in the performance upstream of that stages due to the compressor fouling, loss of efficiency, and many factors that can come into play. The phenomenon that determined the maximum extraction was the choking in the last stage, stage 16. So when the pressure ratio of stage 16 approaches unity, we know that this stage is going to choke and we won't be able to operate beyond certain extraction rate. For that reason, we established that the maximum extraction rate that can take place in that particular design was between 12 to 18%, and it is much lower compared to the zero-D analytical model that predicted it beyond 25%. Then we wanted to know what exactly happens in the back of the compressor at operation like that. So when we approached the maximum extraction rate, here was the 18%. We selected the case with no performance distortion. The maximum extraction was, as indicated previously, dictated by stator or stage 16 choke. That manifested with a very high Mach number, especially in the midspan of the stator 16, and substantial flow separation at stator 16 as well. Then the hub position between the hub and 35% of span of the OGV was occupied by large blockage that contributed to substantial losses, total pressure losses, and entropy losses here. There are some elevated losses as well in the tip region and in midspan of stator 16, as well as indicated in those two figures. Obviously, those effects increase with the extraction rate, and if we go beyond the 18% of extraction rate, we would observe substantial fluctuations of pressure ratio and large instabilities. From technical perspective, that could translate into blade fluttering or uneven forces distribution in the turbine bearings, and many other events that could cause substantial fault of the overall engine. If we have a look at the inlet to outlet static pressure distribution, so left top plot presents the locally average static pressure distribution throughout the back of the compressor from rotor 14 to OGV at several points, starting from a 0% extraction, so like normal operation, and the 18% extraction, so the maximum we could observe. And as you can see, beyond 10% of the extraction, we start to experience pressure ratio below 1 between rotor 16 and the OGV. That informs us it poses a substantial risk of reversed flow taking place in that area, and it exhibits and increases basically with the more and more extraction taking place. So if we were to sum up all those informations that I just presented, the maximum air extraction that was possible from the 0D analytical model perspective was about 29%. However, the 3D CFD simulations that helped us to evaluate this technology suggested that it's not going to be that much. It will be bring down to 12–18% depending on the compressor conditions. So then, when we want to think about the minimum engine load, it was revised down to 24%, from 24% up to 48%. So basically double that what we thought previously. And this is the study for the compressor element only. Please bear in mind that we didn't take into account the combustor, which lies next to it, its stability and emissions that are also the subject of revision when such a substantial change in gas turbine operation method is proposed. The second study that we undertook was the effect of air injection on the flow conditions within compressor. So the question is, okay, we know more or less what happens within the compressor when we extract substantial amounts of air much higher than usual. But then what happens within the compressor if you want to inject this air to elevate the power or boost the power, like to increase the ramp rate? So the initial study done within our numerical model suggested that it will obviously increase the pressure ratio of the overall compressor. That will also reduce the isentropic efficiency of subsequent components, and it will also increase the risk of stall to take place. That was the initial. That were the initial results based on the analytical study. So the questions we really wanted to know to answer in this study is: what's the maximum air injection rate before the compressor stalls, and how does the flow field look like when this event is taking place? So what we did, we deployed the more or less the same CFD model as for the extraction case. We deployed slightly different injection port at the back of the compressor, just behind the OGV, and studied several injection rates ranging from 0 to 30% at different ambient conditions, to see how the high fidelity CFD model will react to such operation. This figure presents the effect of the power of the air injection for power augmentation on the compressor pressure ratio at 3 different ambient temperatures. So basically, we studied the effect of air injection at -5 degrees, 15 and 30 degrees C of ambient conditions, and the effect it had on the stall taking place within the compressor. So based on that, we could tell that the 0D model predicted earlier stall with the reduction in temperature, which is what we could expect, but also similar effect was observed using the CFD. This CFD provided slightly higher pressure ratio than the 0D model, which is an effect of slightly more detailed resolution of flow field, while the 0D uses the map scaling kind of approach. Obviously, we wanted to find out what's going on like locally when we inject more and more air. So this study shows the effect of air injection at the ambient condition of 15 degrees C, so the red line, and what takes place within the compressor from that perspective. So basically, what was important, that there was no like single isolated phenomenon that was typical to initiate the stall. It was rather the worsening of flow conditions all across the compressor. We couldn't identify the region that was like solely responsible for the limitations to take place, unlikely with the air extraction case. Also, when we went above the suggested limit, here was about 60%, we also couldn't find like a specific place or location that would push the compressor into unstable region. But on the other hand, what we found out is that there are some regions, especially in the top and the up, which are occupied by strong reversed flows and substantial blockage, and that reduce the flow area and caused unwanted behavior all across the compressor base, typically visible in stators and OGV, so non-rotating components. Again, on that note, we wanted to understand a little bit more on what's going on from the fundamental perspective. So we took a closer look into the aerodynamic indicators, such as incident angle change. So on the right bottom figure, we can see the absolute velocity change with air injection. Also, the blockage factor all across the compressor. So the blockage factor determines the area of flow that was occupied with blocked cells compared to the overall flow area in given location. It's quite common factor used to evaluate how close a certain compressor is to stall, and the threshold for that value is very much design dependent. For simple geometries of land-based gas turbines like this one, we established that the threshold is 5%. However, for modern aircraft like aero engines, kind of compressor designs, this the value can be much higher, towards 15 or 20 even. So based on those two metrics, not only, but those two I will present here, we found out that 18% of air injection is too much, because it exhibits the established metrics in terms of blockage factor and incidence angle for certain region in the compressor. When it comes to blockage factor, it was substantially elevated, especially in the stators, non-rotating components. However, concerning the incidence angle change, this was particularly visible at the inlet of rotating components, where it exceeded also 5 degrees that was estimated as a threshold for this particular design. And knowing so, we brought back those results and compared it with the 0D model that served as the CFD input. And we found out that regardless of the ambient conditions, the CFD results were relatively close to our initial point, with some marginal differences of design cases, and basically no difference for our ISA conditions of 15 degrees C. So that proves that at some point, well, you never know when the results are. The more fidelity model will bring some substantial increase to your results and credibility. But as in this case, we actually learned what are the flow field features that drive our compressor towards the link. And the last scenario we studied was the air induction for ramp rate improvement. We use the CFD to study what happens within the compressor when we suddenly increase the power. So the previous scenario that we discussed was the effect of air injection for power augmentation with no engine unsteady operation, while this one treats on the engine like quasi-transient study to see if we can utilize the air injection for rapid power improvements and how it affects the aerodynamics of a single compound. So basically, we assume such a scenario. We operate at the minimum environmental load, MEL, so basically the lowest possible operation. Then, rapidly, we need much higher power output to provide for the grid. So what happens next? The air is injected and the power output locally increases. Then with the some air injection going on of local 10% rate, the combustor temperature is increasing, right? So we go along with the power, and then the variable inlet guidelines open, and we restore the required power output. From that point of view, we know that between 180 seconds to 300 seconds that determine the physical time of this engine operation, we know that we can expect some unsteadiness or unfavorable conditions within the compressor due to the stall risk taking place. So what we do for selected time steps from 60 seconds towards 309 seconds of the operations, as indicated in this graph, we selected single points and recalculated them with the CFD method to see how close we are towards the stall based on the established metrics of blockage factor and velocity angle change. So the left-hand side figure presents the blockage factor distribution across the compressor at different times, and the right-hand side change in the velocity angle, so basically the incidence angle of that particular compressor. So the 3D CFD like mimicked some of the operation points which were predicted with the zero-D model. The study supported our suspicions that in the final phase of ramping, between 180 to 310, there's substantially increased risk of stall conditions to take place. However, it's just below the limit, and this kind of operation is possible from the operational perspective. So to conclude this talk, we deployed a 3D CFD study to supplement component level analytical considerations of like selected technology to improve the gas turbine operation. So these were air injection and extraction at various range of the conditions. So what's important, the CFD study helped us to revise the maximum extraction rate from an engine, from the compressor engine, more than by 50%, pointing out the compressor perspective and its stability. However, when it comes to injection rates, the different of design temperatures, the revision wasn't that substantial. It was rather within single percent points with regards to the local master rate, rather than any substantial change. We also identified what are the typical flow features when compressor is approaching certain limit of proposed technology. And that CFD study informed our industrial partner that yes, the investigated concept is possible to work from a compressor perspective, but these are certain limits to which you need to take into account, basically to make sure that you're going to operate it safely. Obviously, as in every piece of research, there is like some further work to do. There is a further work required to evaluate the effect of the injection or extraction of air to the back of the compressor on the combustor component, especially from the perspective of emissions and flame stability, such as. So basically, this was a very good exercise how detailed CFD study can inform industry if the technology they have been thinking about is possible to run, and what are the limitations. And you have a great example of a gas turbine that our center is really focusing into. Okay. This is the last slide of the presentation. I need to acknowledge that the research was funded by EU Horizon 2020 Research and Innovation Grant under program agreement as shown on the slide. The overall project, what I showed you was just a tip of an iceberg, because there were 26 in the end 27 partners all across 9 European countries, and we mutually looked into various technologies that support the European energy transition and facilitate the technologies that basically support the renewables that are more and more dominant in our grids. Thank you.